So the last part of this little chapter is to discuss energy and how energy relates to physical and chemical changes, because there is a component of chemistry that studies that. We're going to start off here in our chapter 10, just doing little bits of chapter 10, so it's really not a comprehensive study of the chapter. And we're going to start by talking about what energy is. So energy, that we know it throughout chemistry and throughout physics, so if you've taken other science courses, you'll notice parallels here, is defined as the ability to do work or produce heat. And so oftentimes this might be what you had down in your notes in other courses. It doesn't really matter if you include this, because really there's two types of energy, and heat is part of one of those forms of energy. So potential energy is the first, and potential energy is stored. It's energy due to position. So maybe something's up at the top of a hill and has the potential to fall down, or composition. And so this is its makeup. And so chemical bonds store energy. So the kind of commonality here is that this is stored energy. And so these ones are kind of good examples. So we have that gravitational energy, magnetic energy, nuclear energy stored in the atoms, chemical energy. So think food energy that your body can digest and break down. Those are all potential energies. Kinetic energy, heat is an example of kinetic energy. And so in this, the commonality here for kinetic energy is that it's all due to motion, or it's all moving energy of movement. And that makes sense when we're talking about mechanical energy, or you running up the stairs or stuff like that. Sound wave is energy waves moving. Electrical energy is the electrons moving in a wire, right? But if we take a look at thermal energy, we really have to narrow our focus down to that molecular level, because as we talked about with temperature, all molecules are moving until they get to absolute zero on that Kelvin scale. And so thermal energy, or heat energy, is what we're talking about here as an example of kinetic energy. So there is a formula, and again, if you've taken other science courses, you may have used that. Physics uses it. These other examples, we do live in a place where we store water, and then water moves to generate electricity. And so that illustrates potential and kinetic energy. In thermal energy, if I take the example of a cup of water, so a cup of cold water, oops, that doesn't say cup, cold water, the molecules would be moving slower, right? So there's a little bit of movement. If we talk about a hot cup of water, on a molecular level, the molecules are moving faster. So here, as comparison, the molecules of water are slower. And so this is kind of paving the way to talk about energy on a molecular level. Okay, so the law of conservation of energy states that energy isn't created or destroyed. It's only converted from one form to another. So we go back to that idea of water being stored behind a dam and then being converted into kinetic energy as it flows through a turbine, and then being converted into electrical energy. These are all examples. So we have this digestion going on here, right, where you take that stored or chemical energy or potential energy and convert it into the energy of movement, which we often think of as a kinetic energy. We have electrical energy becoming light energy. We have photosynthesis here, which is that chemical process that takes the sun and converts it into chemical energy. So plants take and harness that energy and make glucose, so C6H12O6, through the process of photosynthesis. It's the reverse of this respiration process, or that we think of as digestion. Chemical energy can become light energy, right, in your flashlight. In your car, chemical energy can become mechanical energy. Maybe electrical energy can become mechanical energy if you have an electric car or a hybrid. And we also have electrical energy becoming heat, say in a toaster or in uh, a heater of some sort, or a toaster. So in these ones, they all convert. So a lot of these are chemical reactions that convert energy. This one would be a combustion, right? We're burning the fuel to make the car go. So just trying to roll in some of these ones back into stuff we've talked about already. There sometimes are energy conversions in physical reactions, but mostly what we're talking about here are chemical reactions. So the difference between temperature and heat, and I've been really trying to be careful in talking about energy so far. So energy is heat. It's measured in joules, right? It's a flow of energy. Now temperature is like the concentration of that heat energy. So we know that temperature is measured in degrees Celsius or degrees Kelvin in the metric system. And there is a difference. So depending on what it is and how much of it, if I take the Silver King building that I'm in right now, the temperature of the room might be quite cool. But if I compare that to the temperature of a hot cup of tea and talk about how much heat is in the building and how much heat energy is in my cup of tea, there might be more heat energy in the building, even though it's cooler than the tea. And so, you know, it's kind of like wealth. And so wealth would be the heat and temperature would be money. And it's relative, right? 20 bucks to my kid is a lot more than 20 bucks to me. And so, yeah, these analogies can kind of go back and forth and can sometimes help you make some sense of these. The thing that's missing here too is that there is a connection between the energy that goes into something and the temperature change that is manifested. And so different materials can absorb the same amount of energy and have different resulting temperatures. And so what we're talking about with this is just a bit of a side note, specific heat capacity. And a good example of that is if you put a pot on the stove, it's going to heat up really quickly, but you put that same pot with water in it and the water takes a long time to heat up. So the metal has a low specific heat capacity and water has a high specific heat capacity. And specific heat capacity is really that link that goes between heat energy and the actual temperature change that is manifested. So now that we know a little bit about the difference between heat and temperature, let's tie energy back into the state of something. And so these would be physical changes. We've come back to the chemical changes. So physical changes and these changes of state, so just as a reminder, physical changes involve a change in temperature. And so water is our classic example. We'd have cold and hot, right? So ice exists at cold temperatures and water or steam, water vapor, exists at hotter temperatures. Now, as we change states, so as ice changes to water, it's going to have more energy in it. Well, it's going to take that energy from the environment. Same thing goes if you take water and heat it up into vapor, it's going to be hotter, but it's taking that energy from the environment. And so it may be from the stovetop, right? And so all the way this way, we're adding energy in. We would say that this is endothermic. Energy in is the way I think of it, right? That's how we change state. And again, we're talking about physical changes here. If I do this in reverse and go from water vapor or steam into liquid, it's condensing, we know that word. And in this case, we've got more energy and less energy. Well, that energy is going to come out to the environment, right? Same thing goes as we go from liquid to ice, so water to ice, that freezing. Again, there's less energy over here. Well, that water has to go somewhere and it goes to the environment. So these would be exothermic as a physical change. And so exothermic means energy exits. And not exists, exits. Energy does exist. Okay, or energy out. So when we talk about these physical changes, we could also talk about endothermic and exothermic chemical changes. So just to reiterate here a little bit, and hopefully that example makes some sense. All of our definition of systems has kind of two parts. And so we have the thing itself and its surroundings, right? So we talk about the system and its surroundings. So here I said that energy is released to the environment. The environment are the surroundings. If I would talk about the ice and the water and the vapor, those are the systems, right? That's the contents. That's what we're talking about. And so here what we're talking about, and it just put it in more neat terms here, energy flows to change the temperature of something. Exothermic, energy flows out of the system. Endothermic, energy goes into the system, or it's absorbed from the surroundings. And so it flows out of the system to the surroundings. So let's just take a look at these ones and roll it back to chemical reactions. In the lab, we will see some endothermic and exothermic reactions. I would encourage you to check out these that I've put on the Moodle site. They're great examples of really extreme endothermic and exothermic chemical reactions. So as a reminder, in both scenarios, we're not creating or destroying energy, right? It's going to be somehow contained either in the thing or in the environment, right? In its surroundings. And so maybe we're converting potential energy into heat energy or whatever it is. So the chemical energy is transferred to the surroundings as an exothermic reaction, and an endothermic reaction, energy is put in from the surroundings to create that potential energy. And these, like I say, are really good examples of really extreme endothermic and exothermic reactions. In the lab, we'll see our own examples of endothermic and exothermic reactions, maybe not quite as extreme as those two, but nonetheless something to watch for as a sign of a chemical reaction. So in a chemical reaction, if it's happening in a flask, an endothermic reaction, would the flask get hotter or colder? So we have energy going into it. If it's going into the flask, then the flask is going to get colder. If we have an exothermic reaction, if we have energy exiting the flask, then the flask itself is going to get colder. I think I answered this one backwards. Endothermic reaction, oh yeah, the flask is going to get hotter, right? We're putting energy into that. If we take a look at an endothermic reaction, now the surroundings of an endothermic reaction would actually get colder. We're taking energy from the environment and putting it into the system. In an exothermic reaction, we would have things heating up outside, and we would know that it was heating up outside. Sorry for that mistake in there. So one last little bit in our discussion of thermochemistry, and I really just kind of picked and choose from a lot of sections here and really are trying to illustrate two different things. And so when we talk about energy and chemical changes, we're talking about enthalpy. So how much energy is important in chemistry, and enthalpy, or change in heat, is something that we can measure. And so oftentimes it's quantified in joules, or as in change in heat. We also talk about it in change of potential energy. If we graph it, that's something that we talk about. So because joules and heat and energy, they're all in equivalent units, that allows us to be kind of slidey that way. So when we take a look at exothermic reactions, or energy, so in the reactants we have a high amount of potential energy. So these would be the reactants. These would be the products, right? So as this is time down here. So this amount of energy, I'm just going to switch colors for us. So this amount of energy right there, that change in heat is a measure of the enthalpy of this reaction. And so that's what we're talking about. We could talk about exothermic and endothermic reactions because their evaluations as their enthalpy will be different. So just as an introduction. The other thing that we could talk about is entropy. So enthalpy is a measure of energy, and entropy, they're very similar words. Entropy is a measure of chaos or disorder. And so in these ones, we could talk about how things the world tends towards chaos. And so, whoops, this should have been bolded. There it is, entropy. So the level of disorder or matter spread, it says in your textbook. So in this case, we have nice, neat wood. One thing is being converted through the combustion reaction into many other smaller things. There's more disorder in this chemical reaction, and that's the way the world tends. So it takes energy to go back the other way, and so reactions that increase disorder are also favored in chemistry. So your textbook rolls it into some lingo here that I'd never heard of before, but I really think I like it a lot. This enthalpy is talking about energy spread, right? So things tend towards downhill. This exothermic reactions are energetically favored. It's way easier to go downhill than to put energy into something and drive something up the hill, right? Energetically. Matter spread, the other one, is this idea of disorder. And so the world tends towards chaos. Anything that increases the level of disorder, maybe going from one thing to many things, is also favored. And so here we're talking about two different things. Enthalpy is energy spread, and entropy is matter spread. And that's just a little bit of a summary, taking a lot of information from a lot of your sections of your chapter 10 and rolling it together. I left this last little bit in here. It was in the publisher materials, and it's really great information. It's not an articulated outcome, but I really do think that it's worth taking a cursory look through that section, because how this stuff relates to our day-to-day life, I think, is what makes chemistry a more meaningful subject to study.